Good afternoon to all. Continuation of the advanced NMR spectroscopy. Today topic is correlation spectroscopy. Correlation spectroscopy. Simply termed as a COSY. Yes, COSY, COSY. Correlation spectroscopy. So this is mainly two type. Here homocorrelation spectroscopy and heterocorrelation spectroscopy. Here in this case, this represents as a correlation spectroscopy. Here represents both axes as a chemical shift values. Chemical shift values. Chemical shift belongs to identical nuclei. That is a in 2D NMR is called homocosy. If chemical shift represented different nuclei, that is a 2D spectrum of HCAR, heteronuclear correlation spectroscopy. So here this is a mainly correlation spectroscopy. It is represented chemical shift on both axes. Chemical shifts on both axes. Both axes. F1 and F2 axis, both axes. So here mainly two type. Here homocosy, here termed as a HOMCAR spectroscopy. In this spectrum, both the axes H1 chemical shift values, H1 delta CS chemical shift values. In another one, heterocosy, this simply termed as a HCAR heterocorrelation spectroscopy. In this case, one axis H1 chemical shift values and another axis C13 chemical shift values. So in this case, yes, homocorrelation spectroscopy simply termed as HOMCAR. This both the axis proton chemical shift values is taking. And heterocorrelation spectroscopy, this is also termed as a heterocosy or HCAR. Here one axis H1 chemical shift values, another axis is a C13 chemical shift values. Nothing but the here different chemical shift value, here same chemical shift value. Yes or no? So now we are studying the homocosy or homocorrelation spectroscopy. In homocosy, both frequency axis, that is F1 and F2 axis, here contain chemical shift of the protons only. That is a H1 COSY. Yes, this is a homocosy is termed as a homocosy is termed as a H1 COSY. So heterocosy is termed as a H1 C13 H1 COSY. So this is a heteronuclear coupling, here homonuclear coupling. So next year F1 F2 should be taken y and x axis respectively. Mainly F1 is the frequency, one is the taking y axis and frequency 2 is taking in the x axis. Homocosy experiment is used in order to obtain structural information via spin connectivities received by cross peaks. So it gives a here mainly this correlation spectroscopy, that is a homocosy. Now I'm going to explain homocosy spectroscopy. Homocosy in this spectroscopy, it gives information about structural information. It gives structural information via spin connectivities, by cross counterparts. Spin connectivities received by cross counterparts. Received by cross counter spots. Cross counter parts are cross counter peaks. Spots are peaks. So this is a homogosy. It gives the structural information via spin connectivity is received by cross counter peaks or spots. So homogosy spectrum contains diagonally counter spots and counters and off diagonal counters. Counters. So here homogosy, homogosy, homogosy spectrum contains homogosy spectrum contains diagonal counters, diagonal counters and half diagonal counters of diagonal counters. So diagonal counters and half diagonal counters. Half diagonal counters nothing but the cross peaks. Here diagonal counters is nothing but the counters means straight peak. Straight peak. Here cross peak. Cross peak. Okay. So homogosy spectrum contains diagonal counters and half diagonal counters. Diagonal counters gives the straight peaks and half diagonal counters gives cross peaks. Cross peak in the NMR spectroscopy. So next one here homocore spectrum, homocar spectrum or homogosy spectrum gives the information about H1 connectivities. So this is gives the information about H1 connectivities. H1 connectivities. So proton coupling, proton connective give it is related to connectivities is related to coupling nature of protons. Coupling nature of protons. Coupling nature of protons. Related to the coupling nature of the protons. So protons which are undergoing coupling will be present at adjacent positions in the molecule. So protons which are undergoing coupling will be present adjacent positions of the protons. So once again I explain to this one. So in Cauchy spectroscopy, here both axis is a representation, that is a XY axis or F1 F2 axis represents the proton chemical shift values only. So in the spectrum, in the 2D NMR spectrum, chemical shift belongs to identical nucleus, that is a 2D spectrum is called as a homogosy spectrum. If the chemical shift represents different nuclei in 2D NMR spectrum is called as a heterogosy. So homogosy spectrum, both frequencies F1 and F2 frequencies contains chemical shift of protons H1 and H1. So F1 F2 should be taken y and x axis respectively. Y is equal to F1 and x is equal to F2. Homogosy experiment is used to in order to obtain structural information via the spin connectivities received by the cross peaks. Homogosy spectrum contains diagonal counters and half diagonal counters. So diagonal counters nothing but straight peaks and half diagonal counters means cross peaks. Homocar spectrum gives the information of H1 connectivities. So that is it is related to the coupling nature of the protons. H1 connectivities related to coupling nature of protons. So which are where protons which are undergoing coupling will be present at adjacent protons in the molecule. So this is about the which it is about the Homocosy spectrum. So in Homocosy spectrum, two type of the contour peaks is obtained. One is a straight diagonal contours, another one is a half diagonal contours. So this is a I may explain one simple example for the Homocosy spectrum. So this is a 2D NMR spectrum. So in this case, here we have draw a diagonal line. So in this diagonal line, here one spot is there, counter spot, here one counter spot. One counter spot is there, here one counter spot is there. So this is a one of the molecule 2D NMR spectrum. These are the counters are present in the diagonal line, diagonal counter spots. It gives the straight relationship. And if other side of this diagonal line, that is called as a off diagonal line, off diagonal counter spots. It gives the adjacent protons information. Yes. So this is called as a diagonal line. Diagonal line. So this is a diagonal line. Next one, diagonal line. This diagonal line is also divided. Here this is called as a diagonal peak or diagonal counter spot. Yes, diagonal peak or diagonal counter spot. Counter spot. So this is a half diagonal peak or cross correlation peak. Cross correlation peak or half diagonal cross peak. Cross peak. So this is mainly this is a F1 axis taking H1 CS chemical shift value. This is a F2 axis here H1 chemical shift value. So this with respect to here it is obtained as signal. With respect to here obtained as signal. So with respect to this part here obtained signal. With respect to this one obtained spectral. This is a simple representation of the 2D Homocosy spectroscopy. 2D Homocosy spectroscopy. Good, Manjula. These are the cross peaks. These are the state peaks. State countersparts. Here cross countersparts. Please take this one. So in this case, here diagonal line is there. Diagonal line is gives the chemical shift information. Diagonal line gives the chemical shift information. And here half diagonal peaks. Half diagonal counters contains the coupling interactions or connectivity information. Coupling interactions or connectivity information. This is very important. Here diagonal line gives the chemical shift information, and half diagonal countersparts are lines. These are the half diagonal countersparts are lines gives the information is about coupling interaction of or connectivity of nuclei. Connectivity of the nuclei. So this is a simple representation of the Homocosy. Take a screenshot, please. Yes, now I am going to explain examples related to Homocosy spectroscopy. So first example, 2-nitropropane. Yes, first example, example 1, 2-nitropropane. 2-nitropropane. Yes, H3C, CH, CH3, here NO2. So in this molecule, first of all, you are identify the S non-equivalent of the protons. So here this proton, here presence of the plane of symmetry. These two are identical. This A type, this is A type. Here middle is a B type. So total how many type of non-equivalent protons? Two type. So here which is there? Total protons in this molecule, how many? 3 plus 3, 6 plus 1, 7. Yes. Next one, number of non-equivalent equivalent set of protons. How many is there? Here A set and B set. Two sets. Two sets. HA is equal to 6 protons. HB is equal to how many protons? 1 proton. HB is equal to 1 proton, HA is equal to 6 protons. This is A type, here B type proton. So here chemical shift value is influenced by the which group? Electron withdrawing group. Which group? Electron withdrawing group. That is a nitro group. So nitro group. So in this case, here generally nitrogen attached, electron with attached carbon. Here chemical shift value 1.8 to 2.3. Here 1.5. Here 1.5. So here what happened? Approximately HA chemical shift value 1.3 delta ppm and HB proton chemical shift value here 2.1 delta ppm. Next multiplicity calculation, that is M. So multiplicity HA is how many? 6. 6 is directly attached to HB. So this is the which coupling is there? Here vicinal coupling is there. HA coupling with HB. HB is the N is equal to how many? HA coupling with HB. So N is equal to how many? 1. I is equal to proton half. So to N plus 1 rule is applicable. That is a 1 plus 1 here 2. 2 nothing but doublet. So this is a HA proton gives as a doublet. Now HB protons. HB proton coupling with the HA protons. HA protons how many is there? 7. So HB protons coupling with HA. So HA N is equal to how many? 7. I is equal to how much is that? Half. So N is equal to half, that is N plus 1 rule for the multiplicity. So what is the 7 plus 1? It gives as a 8. 8 means octet. Octet, here singlet, here doublet. So octet and doublet is there. Please take a screenshot. So now draw the spectrum. So draw the spectrum. So here which is axis? F2 axis, H1 chemical shift value. Yes. Here which axis? F1 axis. Here H1 chemical shift value. Yes. No positive region, no negative region. Both axes taking H1 chemical shift value. Here how much is there? Here 1.3 here. Here how much is there? 2.1 is there. Yes. 2.1. Yes. In the same axis, here which is there? 1.3. Here 2.1. So one here what is there? Same connectivity. Here this axis 1.3, this axis 1.3. So this is present. Yes. Next to this axis 2.1, this axis 2.1. So here state connection. Next to so this is a HA proton coupling with HB. So there also spot is there. Next to here HB is coupling with the HA. Here also spot. First of all, before the spotting, you can must mention the diagonal line. So this is the same connectivity. Yes, 1.3, here 1.3 present in here. Here 2.1, 2.1 present here. These are the here what happened diagonal countersparts. Yes, direct connectivity information. So here remaining is which is there. So here spot is there, here spot. So then this is a spectrum. 2D. So 1.3 gives as a 1.3. Which one? This one. This gives as a doublet. So dB. Next to here 2.1 single proton gives as a septate. So this is a septate. Next in this case also here which is there 1.3 with respect to this one. Here doublet. So which protons is a doublet? HA is a doublet. Next here septate. Septate. So this is a 2D NMR spectrum of 2-nitropropane. So homocosy spectrum of 2-nitropropane. Please take a screenshot. So this is a yes diagonal spots directly relationship. It tells directly relationship. These are the cross peaks. It is only not gives the direct information, direct connectivity. Your connectivity, your direct connectivity information. This is mainly gives the information about the half diagonal species. Nothing but the group which is attached to next carbon or next to carbon. So this is a which is the 2D homocosy spectrum of the 2-nitropropane. Take a screenshot. Now I am going to one more example related to this concept. So I am giving to the another its isomer 1-nitropropane. 1-nitropropane. Yes, here NO2, CH2, CH2, CH3. So here which is there? Here A type, B type, C type. Yes, A type of proton, B type of proton, C type of proton. How many total protons? 2 plus 2 plus 3. Yes, total protons is equal to 7. Yes, number of non-equivalent protons. Number of non-equivalent set of protons. How many? 3 sets. That is HA protons. How many? 2. Yes, HB protons. How many? 2 protons. Next to HC protons. How many? 3 protons. Next multiplicity. HA is coupling with the HB. Here no. Yes. So therefore here adjacent is 2. 2 plus 1 how much is there? Here 3. 3 means triplet. Triplet. Next to HB coupling with HA and HC. It is coupling with HA and HB. Yes. So here which is there? Here 2. 2. Here this is formula calculation by yes n plus 2ni plus 1 into 2mi plus 1. So this is the both are the non-equivalent is there, or maybe here how many is there? Non-equivalent is 3. Yes, here how much is there? Simply here n plus 1, here m plus 1 rule is applicable. So here a is a 2 plus 1 into 3 plus 1. So 2 plus 1 3, 3 plus 1 4, 3 4 is 12. So instead of the 12, here what happened? Here the 6 protons, here how many is there? Here 2 plus 3 5, n plus 1, yes 5 plus 1 nothing but 6, that is a sextate. So this is a HA protons gives as a which is the sextate. Next HB protons. HA gives as a HA triplet. Next HB is gives as a sextate. Sextate. Next HC coupling with the HB only. HB how many? 2. 2 plus 1 3. So this is also triplet. Triplet. Okay. So this is not correct. You proceed that one. So now we are the arrange the connectivity. Yes. So you take the electron withdrawing group. The protons is a value. If you want approximately, I am taking roughly a 2.1, here 1.6, here 1.2. This is a roughly chemical shift value. Now we can draw the 2D NMR spectrum. So this is a which axis? F1 axis, H1 chemical shift value. So here how many non-equivalent carbons? 1, 2, 3. So this is a HA chemical shift value. HC least one. Next HB, here HA. So here, which is there? H A H HC, here HB, here HE. So here HC mentioned to here HC, HB, HE. So here chemical shift value HC is up here 1.2 delta, here 1.6, here 2.1. Here which is there chemical shift value 1.2, 1.6, 2.1. Here which axis? F1 axis. Here which axis? F2 axis. So here belongs to HA means here HA, here HB, here HC. HC is gives as a 1.2, HC gives as a triplet. Next to HB gives as a sextet. Next to HA gives as a triplet. Next to here HA gives as a triplet. HB gives as a sextet. Here which is there gives as a triplet. So now we can draw a diagonal line. So in x-axis 1.2, y-axis 1.2, both are connecting here. So we can be this is a which is the counter spot. Next to here 1.6 from x-axis, y-axis 1.6, both are the coincide this point. This is a counter spot. Next to here HEA is from the x-axis and HEA from the y-axis, both are connecting here. This is a counter spot. Next here HEA is connecting to the which is there HC is connecting to HB. HB is the this one here. HC is the here HC HB. This is a coincide point. So next one here HB connected with HA. HB connected with HA. Here HA HB HA here HC HC no relationship. Next HB connected with HC. HB connected with HC. Here HC, here HB. So in here HB, HC. Here connected. This is the I mentioned to here. So you connected to these points. Next to this counter spot. So in this counter spot, mainly HA connecting with HB. So this is a counter spot. Next to here HB is connected to HA. So this is a stars indicate the diagonal countersparts and here dots indicates off diagonal countersparts. This is a homocosis spectrum of the 1-nitropropane. Take this one. Please take this one. Yes, Manjula, Meghana, Nikila, Monica, Sweta. Please tell me if you have any doubt. It is clear, ma? Sweta, Manjula. So one axis here, x-axis chemical shift values and corresponding peaks in the x-axis. Y-axis chemical shift value corresponding y-axis. Same y-axis, x-axis coinciding points are appear in the diagonal line, and the adjacent coupling is present in the half diagonal, and connecting this one we get the spectrum. This is called as a homocoursy spectrum. So I am send a few more examples related to this concept. After completion of the class, you can solve the problems. So next, heteronuclear correlated spectroscopy or heterocoursy spectrum. So next one, heterocoursy spectrum or heterocorrelation spectroscopy. Heterocorrelation spectroscopy or heterocoursy. In heterocoursy, here one axis taking as a H1 chemical shift value, another axis taking as a C13 chemical shift value. So here two axis taking as a two type of the chemical shift values. One axis taking H1 chemical shift value, another axis taking the here C13 chemical shift value. So the same carbon, proton, and so now I'm taking the heterocosi spectrum. Heterocosi or ETCAR spectroscopy. Heterocosi or ETCAR spectroscopy. In this spectroscopy, it gives information about connectivity between H1 chemical shift versus C13 chemical shift values. So H1 chemical shift with C13 chemical shift values. So in this case, here F1 axis, nothing but the Y axis taking as a H1 chemical shift values, and F2 axis nothing but the X axis taking as a 13C chemical shift values. 13C chemical shift values. So in this case, no diagonal spots and off diagonal counter spots is appear. No S in this case, no diagonal and no diagonal and half diagonal counter spots. So no diagonal and off diagonal counter spots. This is very, very important. So these are the not appear in the case of heterocosi or ETCAR spectroscopy. Okay. So this is a no counter spots. That is a no diagonal and off diagonal counter spots appears. So counter spots appear at the interaction of the chemical shift of H1 and C13 nuclei. So the counter spots appears counter spots appears at the interaction of chemical shift at the interaction of chemical shift of H1 nuclei and C13 nuclei, H1 nuclei and C13 nuclei counterparts is appear, but no diagonal and half diagonal counterparts appear in this spectrum. So here heterocosi carbon which is not attached to proton will not give to any counterparts. So carbon is attached to protons, it gives the counterparts. If carbon is the absence of the protons, no gives the counterparts. For example, here if you take the ester S, here R C double bond O R. So here carbon no protons, therefore no counterparts. For example, here acetone ketone. So here carbon, here no protons, therefore no counterparts. These carbons no counterparts because absence of the S protons. Please take one. So I'm taking one example related to this concept. So example is a ethyl chloride is taking. Example ethyl chloride CH3 CH2 Cl. So in this case here how many non-equivalent protons? Two set of non-equivalent protons, total 5 protons. Here CH3 one type, CH2 protons is one type. Out of the 5 protons, two set of the protons, and out of the two carbons, two are the non-equivalent carbon. One carbon attached to directly chlorine, one carbon not directly attached to chlorine. Both carbons are different. Here these two protons and the three protons are different. So therefore this is a type of carbon, A type of the protons. B type of carbon, B type of protons. Now we can see the yes, here protons, HA protons, HA protons. This is a mainly coupling with the HB protons. HB protons, how many is there? 2. Yes, 2 plus 1, how much is there? 3. 3 means it gives us a triplet. Yes, triplet. Next to HB protons, HB proton coupling with HA. HA how many? 3. 3 plus 1 how much is there? 4. 4 nothing but quartet. Quartet. Next to Ca carbon. Ca carbon mainly here carbon NMR. The carbon directly attached to protons. Ca carbon coupling with 3 protons. 3 plus 1 which one is there? 4. 4 nothing but the quartet. Ca carbon gives quartet. Next to Cb carbon. Cb carbon gives directly attached protons 2. 2 plus 1 how much is there? 3. 3 nothing but a triplet. Triplet. So here H1 chemical shift value, C13 chemical shift values here. So here chemical shift value of HA proton is this is HA is here 1.5 delta ppm. Yes, here HB is the proton that is attached to chlorine. So this is a 2.5 delta. Next to Ca carbon, this carbon here gives as a 20 delta ppm, 20. Here Cp carbon directly attached to chlorine, here 50 delta ppm. So this is about basic information of this molecule. Yes or no? Here carbon chemical shift value, proton chemical shift value, carbon coupling multiplicity, proton coupling multiplicities. Now we take the spectrum. See here. So in this spectrum, this is a 2D NMR spectrum. So one axis is there. This is a F1 axis. F1 axis taking as a H1 chemical shift value. F1 axis. So H1 chemical shift values. So F1 chemical shift value. Here this is a F1 axis come down from here. Here 1.5. Here 2.5. Next to here which axis? F2 axis. F2 axis is present of the C13 chemical shift values. C13 chemical shift values. C13 chemical shift value, one is present 20, another present in the 50. Yes or no? So 50, 20 is which carbon? 20 is nothing but the Ca carbon. So Ca carbon. Here 50 is nothing but the 50 is nothing but the Cb carbon. Ca carbon gives as a quartet. Quartet. Next one, Cb carbon gives as a triplet. Next one, here Ha carbon, Ha proton. Yes, 1.5 Ha proton. Ha proton gives as a triplet. Next, here is 2.5 Hb proton gives as a quartet. Yes, 2.5 Hb proton gives as a quartet. So now here no diagonal peaks, off diagonal peaks is appear because see here, please carefully. So here carbon connecting with the proton. So carbon connectivity proton 1.5 Ha proton is connecting with the Ca proton. Ca proton here, here Ha proton, here Ca proton. So these two are connecting point. So Ca proton, Ha proton. Yes. So this is a one connecting point. So where is point connecting? Here 1.5 to here. This is a Ca proton and Ha proton. Ca proton chemical shift value what is there? Ha proton chemical shift value 1.5, Ca carbon proton chemical shift value 2.5, 2.0. This is a one counter spot. Yes or no? Next one here 2.5 Hb proton chemical shift value and Cb carbon chemical shift value 5.0. So this is a coincide 0.5. So this is a Cb chemical shift value coupling with the Hb chemical shift value. So there are how many counter spots is there? Only two counter spots is present. So what happened here? Connectivity between spin connectivities between H1 connectivity with C13 connectivity. So this is a which spectrum? Yes, this is a heterocosis spectrum. So heterocosis spectrum of the ethyl chloride. Please take this one. Take a screenshot. Okay, I'm explain one more example. Heterocosis, madam. Heterocosis spectrum. Manjula. Heterocosis spectrum of this compound. Now I am going to explain one example that is related to the heterocosis. So heterocosis is a example is a 1 nitropropane, 1 nitropropane. So here NO2, CH2, CH2, CH3. So now you give the period A, B, C. Okay. So here Ha proton, yes, Hb proton, here Hc protons. Next Ca carbon, Cb carbon, Cc carbon. So here carbon proton chemical shift value, here this is highest, here 2.1 or 2.2, here 1.6, here which is there chemical shift value, here 1.2 around. So here chemical shift value, nitro group is present, electron withdrawing group, this is a maximum present here, 60 or 70 is there, approximately I take 60, here 45, here 25 chemical shift value. So this is taking approximately, not required result. So C13 is a fluctuation that region is taking. So here Ha proton, here chemical shift value. How much is there? 2.2, 1.2 chemical shift value, 1.2 delta ppm, and Ha proton coupling with the Hb. Hb how many? 2. 2 plus 1, 3. Means here gives as a triplet. Next to here Hb proton coupling with the HCA, HC. Here 2 plus 3, 5. 5 plus here chemical shift value where 1.6 delta. So here 2 plus 3, 5. 5 plus 1, 6. Nothing but sextate. Next one, Hc proton. HC proton coupling with only HB. HB how many protons? 2. 2 plus 1, 3. 3 means a triplet. Triplet. Here this is a chemical shift value proton NMR 2.2 delta ppm. Now going to here explain the C13 chemical shift values. Here Ca carbon this one. This carbon is a here chemical shift value how much is there? 25 delta ppm. 25 delta. And this Cb here this Ca carbon directly attached how many protons? 3. 3 plus 1 for quartet. Next to Cb carbon chemical shift value how much? 45 delta. It is directly attached to 2 protons. 2 plus 1 Cb carbon 2 plus 1 3 triplet. Next to Cc carbon here chemical shift value 60. Here this is a Cc carbon directly attached to 2 protons. 2 plus 1 3 triplet. So taking this one we can construct the 2D NMR spectrum. This is a heteroposi. So this axis is a F1 axis taking as a H1 chemical shift values. So this axis taking as a F2 axis taking as a C13 chemical shift values. So here how many values is there? 3 values. 1, here 2, 3. So this is F1 axis here which is there least one 1.2, here 2 1.6, here 2.2. So 1.2 is which protons? 1.2 is a HA protons, 1.6 is a HB protons, 1.6 is a HC proton. HA gives as a which is there? HA gives as a triplet. Next to HB gives as a sextet. HC gives as a triplet. Next to here y-axis taking as a, so in this axis taking as a x-axis, here chemical shift value we can divide equal part. So which is the least one? Least one is a Ca carbon. Ca carbon how much value? 25. That is a Ca carbon. Next to which is there? 45 belongs to Cb carbon. Next to 60 belongs to Cc carbon. Okay, so Ca carbon gives as a which is there? Quartet. Next to Cb carbon gives triplet. Next to Cc carbon gives so Ca carbon, Ha carbon, Ha proton, Ca carbon. So coincide this one. So the chemical shift walls are connected here. This is 2. Next here Cb carbon, Hb proton. So connecting this point. So connected to your chemical shift value. Proton and this one. Next one Cc, Hc carbon, Cc carbon. So your chemical shift value is connecting. So this is a spectrum of the heteroposi spectrum of 1-nitropropane. So connections between x-axis the C13 chemical shift value with respect to corresponding chemical shift value of y-axis of proton. Please take this one. Over. Next to 2D inadequate spectrum. I am explain one example for 2D inadequate spectrum. Inadequate So inadequate nothing but intensive nuclear abundance double quantum transference technique. So 2D inadequate technique here mainly bond connectivity is simply here mainly taking as a proton decoupled C13 NMR is taking in the F1 axis, and F2 axis is taking as a double quantum coherence transfer. Double quantum coherence transfer. So you don't feel difficulty. It is very easy. I'm explain one example. So this is example, that is a CH3, CH3, CH2, CH2, CH3. So this is an N-butane. N-butane, you give the numbering from here 1, 2, 3, 4. So here how many carbon number? Here we give the numbers. Carbon number, carbon number, number of connections. Carbon number, carbon number, number of connections. Carbon number, C1 carbon is there. C1 carbon connecting to the only C2 carbon. So how many connections? One connection. C2 carbon is there. C2 carbon. So this is connected to C1 carbon and connected to C3 carbon. Number of connections is 2. Next to C3 carbon, connections is the connection to C2 carbon, connection to C4 carbon. So C3 carbon connections is 2. Next to C4 carbon, connection to only C3 carbon. So how many connection? 1. So one connection means C1 connection with C2. Here two connections, C2 connection to C1 connection and C2 connection to C3. Next C3 is mainly connection to C2, C4. C2, C3 carbon connected to C2 carbon, C3 carbon connected to C4 carbon. Here C4 carbon connected to C3 carbon only. So no need to any more explanation requirement. It is very simple one, only connections. So now taking this spectrum. So this is 2D NMR. So you are taking as a F1 axis, you are taking as a F2 axis, F2 axis taking as a double quantum S coherence transfer is taking, and F1 axis taking as a proton decoupled C13 NMR. So you give the carbons 1, 2, 3, 4. C1 carbon, C2 carbon, C3 carbon, C4 carbon. Yes, or you mention the based on the chemical shift value. So here C2 is there. Yes, C2, here C3, here C1 carbon is taking. So you can be connected. So C1, C4 no connection. First connection where is there? C1 connection to C3, C1, C2, C1 connection. Next one, which is the connections is present? C1, C2 connection. Next goes to S, C2, C3 connection. C2, C3 connection. Next to C3 to which connection? C4 connection. So this is a which spectrum? 2D inadequate spectrum. 2D inadequate spectrum of the N-butane. So I'm sent to few more examples related to this concept. So all of you solve the examples. If you have any doubt, you can send me message with my personal WhatsApp group. Okay. Thank you to all.